In the previous lecture, we have learned about power series. So we discussed the basic definition of a power series, its convergence, how to check whether the given series is convergent or divergent, and then interval of convergence, means for what values of x the given power series is convergent, and then radius of convergence. We discussed these few things in the previous lecture. So, in fact, the power series is has a form. This thing summation n from 0 to infinity, Cn x minus x naught whole power n. In fact, I should not write it. So this is a form of a power series, and interval of convergence or the radius of convergence is denoted by r. And interval of convergence is, in fact, this is x naught minus r less than x naught plus r, where r is the radius of convergence and this is the interval of convergence. And we have talked also about the convergence at the endpoints. So today we are going to discuss power series as functions. And then we'll see how to solve differential equations using power series. So power series as functions. Any function which is basically continuous can be written as a form in the form of a power series. Function maybe a function y is equal to f of x can be written as in the form of a power series y is equal to f of x, and it can be written as sum n from 0 to infinity Cn x minus x naught whole power n. For example, you might have seen the series expression for some of the functions. For example, e raised power x, it has a series form at this thing x cubed by 3 factorial plus so on. Okay, this is basically, in fact, the series form of the exponential function. You might have studied the Taylor series and Maclaurin series in your A levels. Similarly, sine x has I think x minus x3 by 3 factorial plus x5 by 5 factorial minus so on. Similarly, cosine of x has this 1 minus x squared by 2 factorial plus x4 by 4 factorial plus so on. So these are basically the power series forms of these kind of functions. And these functions are basically differentiable up to certain order. This we'll discuss these things later on in detail, but for now, you just think that any function which is continuous, which is differentiable, or which is continuously differentiable up to certain order, up to nth order, then that function can be written in the form of a power series. Okay? And these are the examples of the functions which can be written as the form of a power series. So we'll discuss it later on. For the time being, you just consider it that any function can be written in the form of a power series. It depends on the function itself as well. Now, if the function can be written in the form of a power series, then the functions are differentiable, obviously, and they are integrable also. So derivative and integral of a power series. Now we are going to discuss these things, derivatives and integrals of power series. Why we need to discuss these things? Because in order to solve the differential equations, we need derivatives of the power series. Okay, so if the power series is this thing, n from 0 to infinity, Cn x minus x naught whole raised power n. If we open it, it becomes C naught plus C1 x minus x naught 1 plus C2 x minus x naught whole raised power 2 and C3 x minus x naught whole raised power 3 plus so on plus any general term Cn x minus x naught whole raised power n plus so on. So we can expand the given series in this form. Now, if y is a function, in fact, it is f of x, then f of x, if this is a function, then we can differentiate any function with respect to x. So it means y dash is equal to f dash with respect to derivative. We are taking derivative with respect to x. So x will be the variable which will be differentiated. Here you have a constant, it becomes 0, plus C1 is a constant. Now the derivative of x minus x naught is 1, plus C2, the derivative of this thing is 2 times x minus x naught, power 2 minus 1, which is 1, obviously, the power rule, plus C3, the derivative of this thing is 3 times x minus x naught whole raised power 3 minus 1, which is 2, plus so on, plus Cn times n x minus x naught whole raised power n minus 1, plus so on. So this should be the derivative of the power series. Now, if we simplify it, what do we get here? C1 plus 2C2 x minus x naught whole raised power 1 plus 3C3 x minus x naught whole raised power 2 plus so on plus n times Cn x minus x naught whole raised power n minus 1 plus so on. Now, if we try to write this power series, the derivative of a power series is again a power series, okay? Because we have powers of x minus x naught here in this series. Now, if I try to write this series back into this notation, summation notation, how do I write? Summation n from now and from 1 to infinity. Earlier, it was n from 0 to infinity because it started from C0. Now, C0 is basically eliminated here. Now, we start with C1. So it can be written as summation n from 1 to infinity. Here, what do you have? 1 dot C1, 2 dot C2, 3 dot C3, and so on, n dot Cn. So this is basically the general term. If we try to write it here, Cn x minus x naught whole raised power n minus 1. So this will be the derivative of this power series. You just take n here, n Cn power n minus 1, and the summation becomes n from 1 to infinity. Okay. But even if you write this summation from 0 to infinity, it doesn't change anything. N from 0 to infinity, n Cn x minus x naught whole raised power n minus 1. Does it change anything? Because when we put n is equal to 0 here, when we put n is equal to 0 here, the first term will be vanished. So even if we take the derivative of this thing, we technically we should write n from 1 to infinity. But even if you write n from 0 to infinity, it doesn't change anything. It will remain the same series as this one above. Okay, now we can take the second derivative of this thing. In the second derivative, C1 will be 0. Here you have 2C2. Here you have 6C3. And what do you have here? Now the y double dash would be f double dash of x, and it would be the summation now in f double dash will start from 2, because the C1 will be 0. This is a constant term. It will become, it will be 0. So the derivative of this thing is 2C2, and the derivative of this thing is 1. So here you have 3 into 2, C3 x minus x naught power 1, and so on. And ultimately here, the summation start from n from 2 to infinity, n into n minus 1 times x minus x naught whole raised by n minus 2. So this will be the second derivative of this power series. Okay. What is basically the difference in the power series when we take its first derivative? We take n down here, n minus 1, and the summation start from 1 ahead, n from 1 to infinity. In the second derivative, you take another power down, n into n minus 1, x minus x naught whole power n minus 2. Now the summation start from 2. Okay, remember these things. So, and also even here, you start with the summation n from 0 to infinity. It doesn't change anything. Does anything change? Will change here? When you put n is equal to 0, here you have 0. So this term will go to 0. And when n is equal to 1, you have n minus 1. Again, the second term will be vanished. And we have basically, we are going to have the same, this one series. Okay, so, but we don't do normally this thing. We write the second derivative in this form, starting from n is equal to 2 to infinity. Similarly, we can take the third derivative. The third derivative of the power series is what? It should be n from 3 to infinity, n into n minus 1 into n minus 2 into x minus x naught whole raised by n minus 3, and so on. We take the fourth derivative and fifth derivative and so on. I hope you get it, how to take the derivatives of the power series. Now, similarly, on the similar lines, we can take the integral of power series by integrating each term with respect to x. If you have any question, you can ask. Now, we need to integrate this thing, f of x, dx, and we have to integrate it term by term. The differentiation of power series is also, we call it term by term differentiation. We differentiate each term of the power series. And similarly, while integrating a power series, we do integration term by term. So we call it term by term integration. So we integrate C naught dx plus C1 x minus x naught power 1 dx and plus so on, plus Cn. In fact, it is constant. We can take it outside so that we have this. We integrate each term of the power series. When we integrate, what do we obtain here? We can have x minus x naught, C naught. C naught is a constant. 1, integral of 1 is, I am taking it x minus x naught. Q, just to be consistent with the other terms. Okay, because it's integral of 1 is x, but I'm taking it x minus x naught so that this term remains consistent with the other terms. Okay, we can take it. There's no problem in it. So similarly here, C1 by 2 x minus x naught whole square plus so on plus Cn by or x minus x naught whole raised by n plus 1 divided by n plus 1 plus 1. So this is basically the term by term integration of the policy. Now, if we want to write this series in the summation notation, how can we write? Now, this can be written in this form, summation n from 0 to infinity, c, sorry, n x minus x naught whole raised by n plus 1 whole divided by n plus 1. Okay, so this will be the integration of basically this power series. It is what the summation remains same, and from 0 to infinity we take the integral of this thing n plus 1 divided by n plus 1. Similarly, we can integrate it again with respect to x, which will have n plus 2 divided by n plus 1 into n plus 2. But the summation notation, so index of the summation would remain same. I hope you get it. If you have any question, you can ask me. If you don't have any question, let's start solving differential equations using power series. Now, the differential equation, second order, particularly second order differential equations, we start with second order, but we can solve any order differential equation using power series. Okay, higher order ODEs means order 3, order 4, order 5. As the order of the differential equation increases, this power series method for solving those equations will complicate, because there will be a lot of series in one differential equation. Okay, so we are for now we are going to solve second order ODEs with variable coefficients. So second order ODE, as you know, we can write it in this form: a2 of x y double dash plus a1 of x y dash plus a naught of x y equal to normally 0, homogeneous ODE. So you start with the homogeneous ODE. Now, we assume the solution of this equation, we call it 1, solution of 1 in the form as a power series what we assume that y is equal to summation n from 0 to infinity Cn x minus x naught whole raised by n is the solution of this differential equation. We assume it. Now, what we do, we insert this solution, series solution, in this differential equation and try to find these unknown coefficients of this power series. Okay, unknown coefficients Cn. Okay, once these coefficients are known, we put again back here in this power series. That will be the solution of the given. Now, in order to find these constants, what we do, we put this into differential equation, and for that we need first derivative y dash to put it here, and we need y double dash to put it here. Okay, so we differentiate y, which will give us n from 1 to infinity cn x minus x naught whole raised power n minus 1 यहाँ पे n भी आएगा, ठीक है. And y double dash, I know it is n from 2 to infinity n into n minus 1 cn x minus x naught whole raised power n minus 2. Now we are going to put the value of y dash and y double dash into this differential equation. Okay. So after inserting these values here, what I do, I try to try to assemble similar kind of terms which which are similar with respect to the powers of x, or I try to simplify the series and try to find these unknown constants Cn. Okay, let us do these things with the help of an example first. Okay, because here the things are unknown. A2 is unknown, A1 is unknown, A0 is unknown. This will complicate our computations here. So let us do these things with the help of an example when we have a particular example of a second order differential equation. So the main idea for finding the solution in this form is this, that whatever the differential equation is, it is second order, first order, third order, fourth order. What we do, we assume the solution in the form of a power series. We take its derivatives, which are required in the differential equation. We insert or substitute these expressions of the series into the differential equation. And then after some kind of simplifications, we try to find these unknown constants. Okay. But as this is a second order differential equation, and a second order differential equation must have a two parameter family of solutions. Okay, because it's a second order, it should contain two unknown constants. Okay, which are basically constants of integration, or you can say two parameter family of solutions. So after inserting these expressions of the series into the differential equation, we normally get two linearly independent series. Okay, we normally get two linearly independent power series as solution of one. Those are the two linearly independent power series solution of a given differential equation. Our general solution would be of this form: y is equal to some constant c1, and first power series. You can say y1 plus another constant plus another power series. You can say it y2. So this is again a power series. Y1 is a power series, and y2 is again should be a power series. Okay. So keep these things in mind. The basic theory of the solutions doesn't change in the power series solutions as well. Okay, whatever the solution you assume, it should contain two parameters. Because it's a second order differential equation, it should contain, we should have two parameter family of solutions. I hope you get it. If you have any question, you can ask me. Now let us do these things with the help of an example. Before starting the example, one more thing which is important, which I should tell you, is the sum of two power series. How to add or subtract two power series. Before starting the example, let us discuss sum of power series. They say it is very important. We'll use it in while solving the ODEs. Sum of power series. Two power series, for example, let we have two power series y is equal to summation n from 0 to infinity, cn x minus x naught whole raised to power n, and another power series y is equal to n from 0 to infinity, dn x minus x naught whole raised to power n. Okay, these are two different power series, but their interval of convergence with a same interval of convergence. If their interval of convergence is same, then they can be added. And they will be added in a way that same powers of x minus x naught should be added to correspondingly. You can say that. So if we have c naught, which doesn't have any x, c naught should be added to d naught. And c1, whose power is x minus x naught power 1, it should be added to d1, whose coefficient, which is the coefficient of x minus x naught whole power 1. In short, the series are added term by term in a way that we add the coefficients of like powers of x minus x naught. So y, if it is y1, it is y2, then y is the sum of y1 plus y2, so that summation like powers of x should be added to the similar powers of x, and also the summation term, they should have the same index as well, okay? Or the initial and final values of the sum, they must be same. Index could be different. For example, this thing can be written as sum k from 0 to infinity dk x minus x naught whole raised to power k. So the index is in fact dummy. You can write any index, k, p, l, anything, but their initial and final values and the powers of x, they should be identical. Okay. So here we can write, if we have n is equal to 0 to infinity, and here we have n is equal to maybe 1 to infinity, then we cannot take common this summation. Their starting and ending values, they should be same. So here we have n is equal to 0 to infinity, cn plus dn, the coefficients of like powers of x should be added. So this is how we add two power series. Now, let us have an example of this thing. How do we handle when at least one thing or both things are different in two power series? Yeah, yes. Example, if we have two power series, let us assume that this is n from 2 to infinity, and times n into n minus 1 times cn x raised to power n minus 2. This is the first power series, and the other power series is maybe summation n from 0 to infinity cnx power n plus 1. Okay. Now we have two power series. This this is y1 and this is y2. We need to add them. But here you can see that the index of this summation starts from 2 and index of this summation starts from 0. So we cannot take these two summations outside. Okay, we cannot take them common. Similarly, the power of x is n minus 2 here, and the power x is n plus 1. So we cannot take it common. How do we add them? Let us y is equal to y1 plus y2. It should be n from 2 to infinity, n into n plus n minus 1, cn x minus n minus 2 plus summation n from 0 to infinity, cn x power n plus 1. Okay, we have added them. Now let's see what we do here now. What we do in this situation. Now you can see that n start from 2 and n start from 0. We cannot take it common. And power of x here, the power of x in this series starts from when we put n is equal to 2. When we put n is equal to 2, what do we get here? X power 0. So the first term of this power series is x naught. And the first term, whenever we put n is equal to 0 here, what will be the first term here? X power 1. So the first term of this power series starts from with x power 0, and the first term of this power series starts from x 1. So there is a difference. Okay. So what we do here, we expand only the first term of this series. Okay. What we put here, n is equal to 2. What we get, 2 times 2 minus 1, c2 x power 0, plus only the first term I have opened, only the first term. The remaining series will start now n from 3 to infinity. Rest of the things will remain same. Plus now we will add these two series. Okay, we'll leave it. We leave this term as it is, as the first term here. Now you can see that this power series starts with x1 now, and this power series also start with x1. Now the powers of x are similar now in these two power series. Now what is left to make identical? Now we are going to make the summation term identical in both series. Means identical means we are going to make n the summation index, they should start from the same initial value. For this, what we do, we change it. Sorry. We are going to change the index now. Okay. How do we change it? We write it n is equal to 3, which implies n minus 3 is equal to some other index k maybe. Okay. किसी एक को change कर ले. ठीक है. You don't need to change both, or you can change both as well. ठीक है. अब यहाँ पे n is equal to 0 से start हो रहा है. We cannot make any substitution. Okay. अब आपने यहाँ पे n, या वैसे ठीक है, ये भी ठीक है. It's okay. You can only change this summation notation into this. Okay. You are going to change it n minus 3. Sorry, n minus 3 is equal to k. Now you are going to change the index in this way by inserting this thing. Okay. Either there are two methods, in fact. Either you use this thing, or you use this thing to change the notation. You can also put n minus 2 is equal to some other index p. Okay. In that case, in this case, when if you use x power something, in that case you have to change both exponent of x. Okay. In that case, you also have to put n plus 1 is equal to some other maybe l. Okay. अब दोनों आप चेंज करेंगे तो आप देखेंगे एक्सपोनेंट भी सेम हो जाएंगे और समेशन टर्म विल आल्सो बिकम सेम. Okay. But for the time being, I'm going to change this one. Okay. अब ये वाली जब ये सब्स्टिट्यूशन करेंगे यहाँ पे तो आपके पास क्या होगा, क्या आएगा? So in the first series, this thing, we are going to make this substitution. N minus 3 is equal to k. Now we are going to change the summation values. If n is equal to 3, जब n 3 के इक्वल होगा तो k किसके इक्वल होगा? When n is equal to 3, k must be equal to 0. And infinity, if n is equal to infinity, then k should again be infinity. Okay. Now the summation term has been changed from n minus 3 to k. So k is from 0 to infinity, because when n is 3, k is 0, and when is infinity, k is infinity. So the summation term of this series has been changed to this thing now. And n is equal to k plus 3. Okay. From this substitution, I can find here, let me write it. N from this equation, what we can find, n is equal to k plus 3 and n minus 1 is equal to k plus 2, because we take minus 1 on both sides. अब हम इस पावर सीरीज को कैसे लिख सकते हैं? It can be written as k from 0 to infinity, and n की जगह क्या लिखेंगे? k plus 3, और n minus 1 की जगह क्या लिखेंगे? k plus 2, और यहाँ पे cn की जगह c k plus 3 and x power n minus 2 है, तो n minus 2 क्या होगा? K plus 1. So this is k plus 1. Now you can see that this series is now identical to this series. How? K is a dummy index. We can change k to हम k की जगह n लिख सकते हैं, n from 0 to infinity, n plus 3, n plus 2, cn plus 3, x power n plus 1. अब आप देखें ये सीरीज थी, it becomes now this thing. इसमें समेशन टर्म इसकी समेशन टर्म के इक्वल है, और इसकी x पावर n plus 1 इसकी x पावर n plus 1 की इक्वल. Now you can sum them. ठीक है, इनका हम sum we can find the sum easily. Now the sum of these two series would become 2 into 2 minus 1 is 1, and c2 यहाँ पे 2 c2 आ जाएगा, plus sum n from 0 to n from 0 to infinity. आपने sum दोनों में से कॉमन ले लिया, और पहली सीरीज में आपके पास n plus 3, n plus 2, cn plus 3, और फिर आपने x पावर n plus 1 कॉमन ले लिया, प्लस दूसरी सीरीज में cn और x पावर n plus 1. This is how we add two series now. उसके जो कोएफिशिएंट्स हैं वो हमने ऐड कर दिए, x पावर n plus 1 दोनों में से कॉमन ले लिया, और समेशन दोनों में से कॉमन ले लिया. So this is how we can add two series. I hope you get it. If you have any question, you can ask me. This was the first method that we can change the index of first series to make it identical to the second series, or we can make a substitution in both series, which comes from this exponent term, power term. We try to make substitutions of these power. N minus 2 is equal to some other k index, n plus 1 is equal to some other p index, and then we try to make these substitutions. Then both series will have identical exponents, x powers, and as well as the index in the summation will start from the same point to infinity. Okay, तो दूसरे मेथड से भी हम ये कर सकते हैं. Try to make their summation indices and their exponents same by using these powers in x. Okay, try to make them identical, try to take their sum in your free time in the evening. If you find any difficulty, you can ask me any question. I'll definitely discuss with you in the next lecture. Now it's time for the quiz. I think the quiz will start at 8:45. I'm going to give you a very, now let us discuss the example of the differential equation. How do we solve it? There are a couple of more examples of making these indices same in my notes. You can see them, and then you can ask me any question in the next lecture if you don't understand anything. Okay. Now let us discuss very quickly an example. We'll discuss other things in the next lecture, existence or some other thing. We need to solve the following differential equation: y double dash plus xy equal to 0 using power series method. Using power series. What we do, we assume the solution in the form of a power series, and from 0 to infinity, Cn x minus x naught whole raised to power n. Okay. Normally, this point is given. It is an ordinary point. I shall discuss it in the next lecture. We assume that x naught is 0 here. Okay. In that case, if x naught is 0, then I'm left with Cn x power n. Okay. Now I'm going to put this series into this differential equation. I need y dash, which is n from 1 to infinity, n Cn x power n minus 1. And I need y double dash, so which is n from 2 to infinity, n into n minus 1, Cn x power n minus 2. So I'm going to insert these three things here. In fact, two things, because we don't have y dash, luckily, here. So I only put y double dash and y here. So the left-hand side basically gives us y double dash. Yeah, 0 के equal put कर देंगे इसको. Don't worry about it. So y double dash put करेंगे तो क्या आ जाएगा इस equation में? N from 2 to infinity, n into n minus 1 Cn x power n minus 2 plus x times summation n from 0 to infinity Cn x power n is equal to 0. Okay. Now this x has nothing to do with n. We can take it inside as well. So this can be written as n from 2 to infinity, n into n minus 1 Cn x power n minus 2 plus summation n from 0 to infinity Cn x power n plus 1. Here we had x power n, and this x power 1. The bases are same, exponent will be added, so this becomes equal to 0. Now, these two series have different index. N from, it starts from 2 and n starts from 0 here. And the exponent powers of x are also different. What we are now going to do, we are going to make these two things identical, and then we'll add them. And then we'll try to solve coefficients by comparing it to the right-hand side. We'll start this example from here in the next lecture. Now, for today, I'm going to stop it here because we have a quiz. So Okay, then I'm going to stop it here. You can start your quiz.